In this next chapter, we're going to be working with benzene and some of the reactions that benzene will undergo. The big thing to keep in mind is that benzene is unusually stable, and we already learned about that and know that this stability is due to aromaticity. So one of the things you want to keep in mind is that the reactions that benzene does actually retains aromaticity in going from the starting material to the product, and we'll see that. So benzene doesn't react like typical alkenes. For example, we know that if you have cyclohexene and you react that with Br2, the bromine adds across the pi bond, and you get this bromination product. And you might expect the same thing to happen with benzene because it does have pi bonds. But if you just take benzene by itself and treat it with bromine, no reaction occurs. What we do find, however, is that benzene will react with both nucleophiles and electrophiles under the appropriate conditions. So here bromine's acting as an electrophile, but the conditions just aren't right. It's not electrophilic enough to react with benzene, but there's going to be a way that we can make this happen. As I mentioned previously, reactions that retain aromaticity going from the starting material to product are favored. Now, that's not to say that you may not temporarily lose aromaticity during the course of the reaction, but as long as the starting material is aromatic and the product is aromatic, there's a chance the reaction can occur. So there's two main classes that we're going to look at in this chapter. The first is electrophilic aromatic substitution. And just like the name implies, we're substituting the aromatic ring with an electrophile. So in the most simple sense, if we just start with benzene, and we react that with, just going to use a generic E+, and I'm also going to draw in just one of the hydrogen on the ring. And this is the hydrogen that ends up getting substituted. So basically, a pi bond to the ring attacks the electrophile. You get an intermediate. That's just like what happens when you attack any pi bond with an electrophile. Put the electrophile here. We still have the hydrogen and a carbocation. Now, this intermediate doesn't have aromaticity right now, but what always happens in a final step is something with a lone pair of electrons will act as a base, and this step is always very rapid. That will take the hydrogen off of the ring, moving those electrons back down to form the pi bond. Giving you the electrophile on the ring. So we substituted the hydrogen with the electrophile. In terms of terminology, we often just abbreviate this process as an EAS reaction. We're going to see examples of substituting with halogens, nitro groups, sulfur groups, and even carbon groups. The second type is nucleophilic aromatic substitution. And in the most basic sense of this, you're going to have an aromatic ring that has a halogen attached. Let's just say a chlorine, for example, because we need, for this reaction, we need a leaving group. And what's going to happen in this case, and as you'll see when we get into the actual nucleophilic aromatic substitution reactions, that there's often other electron withdrawing groups on this ring to help the reaction out. We're keeping it very simple for now. We're going to use a nucleophile, and I'll just be generic with Nu minus. In this case, the nucleophile attacks the ring at the carbon containing the leaving group. Push those electrons onto this carbon as a negative charge. We still have the chlorine, and now the nucleophile added here. Again, we've temporarily lost aromaticity, but what happens in this case is this negative charge comes down, or that lone pair comes down to reform the pi bond, and you lose your leaving group. So in this case, we substituted the chlorine with the nucleophile.